Now, in this part of the series, we're focusing on something every technician works around constantly, air. So it doesn't look like much, but air is the largest insulation system in the entire power grid. So almost every clearance, every overhead line, and every open switch relies on air's insulating strength. But air is not perfect insulator, so it has its limits. Once the electric field crosses certain thresholds, air behaves in predictable stages: ionization, avalanche, formation, streamer, growth, and full breakdown. Now, if you understand these stages, everything from corona to lightning flashover becomes much less mysterious. So let's start with the simplest idea. Air normally keeps charges separated. Its molecules are stable as electrons are tightly held, and under normal conditions, nothing conducts. But the moment the electric field forms around an energized conductor, the molecules start to feel forces trying to pull those charges apart. Now, electric field strength depends on geometry. So if you take a perfectly smooth sphere at some voltage, the field is evenly spread. But if that sphere becomes a sharp point, the field becomes much stronger in that tiny region. That's why a small connection mistake in the field, like a frayed strand or a sharp burr, can cause localized corona even when the rest of the conductor is fine. Now, what actually happens inside the air when the field becomes strong? The first step is ionization. So fast-moving electrons collide with air molecules and knock off more electrons. So this is called the impact ionization, and it's the start of the avalanche process. Now, as the field grows, each electron causes multiple new electrons, which causes more collisions, and the growth becomes exponential. So this is the avalanche region, still small, still local, but now the air is beginning to respond electrically. Now, if the field keeps increasing, avalanches begin to link together into a structure called a streamer. Now, a streamer is a finger-like channel of ionized air that extends toward the opposite electrode. It's not a full arc yet, but it's a highly conductive path that's preparing the way for one. Now, in fact, the most dramatic example of streamers is lightning. So long before a lightning bolt touches the ground, millions of tiny streamers, called leaders, step downward through the air in segments. So they change the direction, branch, and probe the electric field until they find a path that can support a full breakdown. Now, in a power system, streamers aren't usually that large, but the physics is the same. So when a switch opens under the high voltage, or when the conductor has a sharp edge, streamers can appear long before a full flashover. Now, once a streamer connects to the gap, the resistance drops dramatically, current surges through the channel. The temperature spikes to thousands of degrees and air becomes plasma, and now you have a full arc. Complete breakdown of the air of the insulation. But what makes the air so interesting is that you don't need a perfect storm to see these effects. You can see early stages of breakdown in many everyday power systems conditions, especially corona. Now, corona is stable, partial breakdown of air around the conductor. It happens when the electric field is strong enough to ionize air near the surface of the conductor, but not strong enough to form a streamer across the entire gap. Now, corona forms a faint glow, usually bluish or purple, and you'll see it on high voltage lines at night, around bushings, or on a conductor hardware when the geometry is smooth. Now, corona usually isn't dangerous by itself, but it does cause problems. So it creates audible noise, it produces ozone. More importantly, it wastes energy and accelerates aging of nearby insulation. So that's why utilities spend so much time designing corona-free fittings, grading rings, and hardware shapes. Now, another key idea is that air breakdown doesn't happen at one fixed voltage. It depends on the distance between electrodes, the pressure, and the gas composition. This relationship is shown in something called the Paschen curve. So the Paschen curve shows that air usually becomes easier to break down at certain combinations of low pressure and small gap distance. So that's why aircraft, mountaintop substations, and even test labs at high elevations use correction factors when determining clearances. But most technicians deal with air behavior that's dominated more by geometry than by pressure. So for example, a flat to flat gap might withstand tens of kilovolts without any corona. But introduce a sharp corner or a stranded conductor and the local field strength can double or triple, and enough to produce corona even though the overall voltage hasn't changed. Now, this is why the field hardware is rounded, smooth, or fitted with corona shields. It's all about distributing the electric field so no single location becomes overstressed. Now let's connect this idea to switching devices. So when a disconnecting switch opens under voltage, the contact point becomes a sharp gap moving through the air. And as the gap widens, the electric field initially increases before eventually falling. So for a moment, the geometry is ideal for streamers and arcs to form. And that's why opening under load or under trapped charge can create visible arcs. So even if the switch was never designed to interrupt current. Our air breakdown also depends on polarity and shape of the applied voltage. So lightning impulses, fast front, short tail, create steep field gradients that encourage streamer formation. Switching impulses, slower and longer, test the endurance of air insulation under sustained stress. So these different behaviors are why equipment is tested with standards 1.2 per 50 lightning impulses or 250 per 2500 switching impulses. So what does all of this mean for technicians in the field? It means air insulation isn't random, it follows predictable rules. When you hear coronas, see small surface glows, or notice arcing during switching, it's because the local electric field exceeded what the air can handle. It also means that maintaining clearances, avoiding sharp projections, keeping hardware clean, and inspecting conductor surfaces are essential tasks. So every bit of geometry affects the electric field, and every electric field affects whether air can continue functioning as reliable insulation. In the next part of this series, we'll move deeper into real equipment and look at how solids and liquids behave as insulation. They fail differently than air. They deform, age, trap moisture, develop voids, and sometimes fail quietly long before anyone notices. And that video will connect directly to partial discharge and long-term insulation reliability.